Okay, so now we want to talk about molarity, but before that we need to understand the meaning of concentration. Okay, so what is concentration? So whenever you're talking about concentration, basically you're trying to talk about trying to figure out how much has been dissolved in a solution. Okay, how much is dissolved in a solution. It may be in terms of moles, it may be in terms of mass. Okay, so there are different ways in which we can express a concentration, but basically we talk about it in terms of the amount of solid dissolved in what, in a given volume of what, in a given volume of what, a solution. That's what we get to talk about. So now this concentration may be expressed in different forms, and the most common way that you're going to find it, we get to express concentration in terms of the number of moles dissolved in what, in a volume of a solution. That's what we get to talk about. Are we together? So concentration is given as the number of moles over volume there. So now what gets to lead us to molarity? What's the difference between concentration and molarity? Is there any difference? What's the difference? I'm very much interested in knowing the difference between the two. Anyone? To help us define molarity. Okay, so you guys, you're quiet. So you've said there's a difference, but you're not telling us a difference. That is, so molarity basically gets to be. It turns out molarity is just concentration itself, except it is interested in specific units that we get to talk about. So when you talk about your moles, and the volume that you get to look at under molarity is given in terms of what? What are the units? What are you interested in under molarity? What are the units of the volume that you get to work with? Let's hurry up, guys. We talked about some of these things. I'm sure you do have ideas. So I'm waiting. It's a liter. Okay, so you can think of it in terms of a liter or decimeter cubed. So now what are we trying to say? So we are trying to say a liter is basically equivalent to a decimeter cubed, right? So whenever you get to other units, the number of moles dissolved either per liter or moles per decimeter cube. This is what we are calling what? This is what we are calling molarity. So now molarity is a way of expressing concentration. So instead of you expressing or showing these units, for example, in a case where you are given to say you have about 0.4 moles dissolved maybe in 4 liter, in a 4 liter concentration also. Okay, so how do you get to determine the concentration in such a case, or how do you get to determine your molarity? So we can say our molarity or our concentration is basically going to be given in terms of the number of moles that we have over what, the volume in liters. So we have 0.4 moles divided by what, 4. What are we going to have? 0.4 divided by 4. So remember our units are, we have liters, then we have moles. So what are we going to have? 0.4 divided by 4, is that going to be like 0.1? So it's 0.1 moles per what? Per liter. So now I want you to know that instead of you showing moles per liter, you can also present your solution as what? 0.1 with a capital letter what? M. So it indicates, even when you're given I'm sure you saw some questions where they just give you 0.1 molar. I think I saw 1 molar concentration. That was like on question 6 for chemistry 1010. So you need to understand that it means moles per liter or moles per decimeter cubed. Now, in a case where they get to give you something different, maybe they give you to say you have 0.4 moles again, but then the volume they tell you have 100 cubic centimeters. So you need to be very careful. They ask you to find the molarity there. You need to be very careful. You need to look at the units. So now cubic centimeter is different from the decimeter cubed or a liter. So you need to know the conversions there. That's why we are talking about the measurements at the start of this topic. So we said 1 decimeter cubed or a liter is equivalent to how many cubic centimeters? What did you say? Okay, so it's equivalent to 1,000 cubic centimeters. So now, how do you get to move from the cubic centimeters going to our liters? So if you put it this side, this is what you know, but I don't like this. You should stop using that. So think of it in this way. You can say, okay, you have 100 cubic centimeters. And what do you want to see? You want to see liters, right? So you can multiply by a liter. Now, this is supposed to be divided by the equivalent unit, which is like 1,000 cubic centimeters, so that you're able to see the way they're cancelling out and you stand out with what? A liter. Or if you want, you can work with the ratio, whatever works for you, but I feel this is faster and it makes more sense. Okay, so what are you going to have? 0.1, right? Liters or decimeter cubed. So at that point now, you should be able to do what? You should be able to determine your concentration. So our molarity is going to be given as what? 0.4 moles divided by what? Divided by 0.1 liters. And in such a case, we have 4 molar concentration or mole per decimeter cubed. Does that make sense? Any questions? Now we together? Okay, so I'm starting from these basic questions that you can be asked before we get to look at the complex ones. So make sure you just pay attention, you get everything that I'm saying. What if we change the question and talked about a concentration of 0.2 molar concentration, and then we get to talk about you determining the number of moles given a volume, maybe let's say of can talk about 9 by 10 to the power 3. Maybe we talk about okay, let me not complicate it. Let's say we talk about 9 by 10 to the power 3 as it is, or let me just say 9 okay, we'll go for 300 cubic centimeters. So determine the number of moles. That's a question. What are we supposed to do? So what have we said? If you talk about our formula, we said that concentration is given as what? Number of moles dissolved in what? In the volume of the concentration. So basically, how do you get to determine the number of moles then? Anyone to tell us what to do there? From what we've talked about? Okay, so it's going to be what? Okay, I like your formula, but then it's okay. Yeah, it's very fine. But then I want you guys to work with this method, dimension analysis, because it helps you out. And if you get it, it doesn't need you to memorize any formula. I'm writing the formulas for now because we are not yet used to this way. That for the sake of what is coming, we need to understand what I'm trying to show you. So now, how can we simplify with 0.2? We know it's what? 0.2 is mole per what? Per liter, right? Or decimeter cubed if you want. So now, what do we want here? We want to come up with a number of moles. So like on top here, what we have is, we have moles already. 0.2 moles dissolved in what? So 0.2 moles in a liter. That is the concentration that we are given. So we don't want to see the liter there. We are just interested in number of moles according to the question. So we want to do something so that the liter can be cancelled out. And so we multiply by 300 cubic centimeters. So now we are not interested in the cubic centimeters. Why? We want to see a liter. Okay. want to see a liter so that it gets to cancel out with a liter that is on the bottom there. So in short, it requires us to convert the cubic centimeters to liters. And we've said, since we want to see a liter on top, we've said in every cubic centimeters, like in every liter you have 1,000 of those. So that we can divide the 300 by 1,000 and these units will go. If we understood what I've done there, I've just like converted the 300 to liters, then I need to multiply according to the formula that you guys have given me. You've told me your number of moles is basically the product of concentration and what? And volume there. Are we guys together? Are you following me? Or maybe... Okay. Am I too fast? Oh, you have a question? Okay, did you just join the class? Okay, is there anyone who got what I said? Which is in terms of what now? What does it, like, how do you, yeah, yes, you're right, but then, how can you simplify it so that somebody is able to see the actual units involved? Okay, moles per liter. And this is what this is exactly what we have on our left there. Okay, any questions? So let's get our calculators and get to do the calculations. So for you, we have 2 zeros there I can cancel out. So we have like 3 divided by 10, that is going to be like 0.3. Then 0.3 multiplied by 0.2, that is like 0.06, right? So moles. Any questions? Do we have any questions? Okay, assuming there are no questions, we can proceed. We begin advancing now. Yes, I'm getting you. Okay. Okay, so well, yes, yes, yes. You're right. We're trying to review it before we get to proceed to... Pardon? Basically, it's molality. Yes, yes. Okay, let's try to advance now. Let's say you have 500 grams of a sample of potassium phosphate, sorry. Potassium phosphate. So, you have 500 grams of potassium phosphate. Who can give us a formula for the potassium phosphate? So that much is dissolved in a 1.5 liters. What is the molarity now? How do we get to find it? So before we get to do that, we need to understand we need to know the formula of what? The formula of potassium phosphate. Anyone who knows what the formula is? To give us the formula for potassium phosphate. So for a phosphate is basically K3. Okay. So this is coming from the fact that a phosphate is basically a radical that comes with a variance of what? A 3 minus, right? Then this comes with a 1 there. So if you get to combine them, that's where the 3 is coming from. They'll get to exchange and phosphate will just remain as it is. Okay, so now, who knows? What are we supposed to do? We are saying molarity is given as what? So now, this is where you need to understand everything that you're learning, because they'll combine different concepts in one question. They won't want to ask you to determine the number of moles, but they'll ask you to find molarity. And they're not going to give you the number of moles and the volume in the actual units. They'll require you to do something about it for you to be able to do that. So in this case, we realize that, of course, we do understand molarity is given as number of moles dissolved in a liter of a solution. Of course, we've been given our liters where we are given our liters. But are we given our moles? We are not. So we've been given the mass there. So how do we get to find the number of moles using the mass? Anyone with an idea there? Okay, so we go back to now the concept of mass over molar mass, right? Okay, so now what do we have here? We've been given the mass already. We need to find what? We need to find the molar mass from the formula. That's why I was asking for the formula of this compound. So let's get to determine the molar mass of potassium phosphate. So if you check your periodic table, what is the molar mass of potassium there? Okay, potassium. Oh, sorry, phosphate. At phosphate. Phosphorus, sorry. Phosphorus. Okay. Then oxygen, I think that is common, 15.9994, right? Okay. So as you get to work with these figures, I'm sure you'll be able to even remember them, even without checking a periodic table. So do more calculations. Now, if you're cruising to atomic structure, you'll find that 70% of the questions that are going to be in test 1 are going to come from from stoichiometry for your own information. Okay. And the lab is also going to come from stoichiometry. So make sure you understand your titrations and what we are doing. Okay. So that is not to scare you, that is to remind you that don't rush. The lecturers may be rushing, but make sure you understand everything before you proceed at your personal level. Okay. Alright. So what are we getting after doing our calculations there for our molar mass? Anyone who has done the calculations? Sorry, calculator. 2 point what? Okay, so that's I've gotten just about 5 figures of your solution. So we have our molar mass there. So what are the units? Grams per mole, right? Okay. So now we have our mass there. So 500 grams multiplied by the molar mass. Is it multiply or dividing? So we need to multiply by reciprocal because we are dividing. So it will be a mole over what? 212.26 grams. Any questions, sir? So what are we getting as our number of moles after dividing 500 by that? Okay, so I'm basically getting a 2.36. I'm getting 2.3556. Okay, so these are what? Moles, right? So what are we trying to find now? We're trying to find molarity. So we said our molarity is going to be given as the number of moles over what? What is our volume is given as 1.5 in liters already, so no need of us doing any conversions here. So now what are we going to get after dividing by 1.5? Anyone who has done the calculations already? 1.57. Okay, 1.57. Okay, cool. But then, how many significant figures do we have in our data there? The first figure what we were given in the question was 5.00 grams. I want to show you because I know we are very much interested in that. So then we also had 1.5 liters. So I told you guys how to, I'm sure you've watched either one of my videos on that. So how do you get to determine the number of significant figures in this figure? How many are there? So we have 1, 2, 3, 4. Is that true? Is that okay? There are 4. Ah, okay, cool. Okay, there are 3 significant figures. How many significant figures are in 1.50? Don't question me yet on the first part. Just tell me for the next value that we have. Okay. So now, what's the difference? Why have I said that one is significant and this one is not? Okay, so make sure you pay attention to the rules that you're being given under the significant figures. They're going to tell you, of course, a 0 after on the right of the decimal number is significant if it comes after, when there's a number before the decimal point on the left. So if you have 2.0, I can tell you that that one has got 2 significant figures. Okay, but if I give you if I give you, for example, 0.01, how many significant figures are there? There's 1. Why? Because the point is coming after what? After a 0. So if you have 20.0, it has 2 significant figures there. Are we together? So this 0 that comes after a decimal point is only significant. Listen, the 0 that comes after a significant figure, or that comes after a decimal point, is only significant if it comes before a number. So if you talk about this value that was given in the question, what was given? 1.50 liters. So I'm saying this 0 is significant because there's a 1 this side. Are we together? So you have if you have 2.00, all these are significant figures because there is a 2 before a decimal point. But if you have 20, for example, 20, zeros coming this side will only be significant if there is a number this side. That's when these zeros can be significant. But if there is nothing, they are not going to be significant because they are coming after a 0 there. You can research and get back to me if you want. Is that okay? Yes. So I'm sure I can send you the notes after that. So you need to understand that basically when you're talking about zeros, basically they are the ones that get to shake you in terms of being able to determine the number of significant figures. When they're in between numbers, they are significant. Zeros before a decimal, yes? It's saying four significant figures. The notes that you got from... Okay, I'll get back to you on that one. I'll get back to you. But I do have proof that basically they are not significant figures. Okay, anyway, that's not our topic this night. So we had 500.0, right? Then which other one did we have? We had 1.50 liters. Okay. So which one has got the least number of significant figures? So this one has got 3. So according to what you're saying, you may consider that to be 4 if you want. So either cases, the least number of significant figures remains to be what? Remains to be 3, not so? And that's why our solution will still remain to be 1.57 molar concentration. Okay. Any questions there? Are there any questions? Siame, are we okay now? Okay, let's move. So now, apart from you guys understanding what basically molarity is all about and what's not, we need to understand what happens if you have let's say, as we have from looking at the previous question there, what did we determine there? We've determined our volume was given to be 1.50 liters, right? Then we've determined that our concentration is 1.57 molar concentration. What happens if we come to add water there? We add water. Let's say you add water of about 200, maybe 200 cubic centimeters. Do you expect the concentration to remain the same, or something will change about it? Okay, thank you very much. So, look at this relationship that we have there. So, an increase in volume will reduce what? The concentration. Are we together? So, maintaining the number of moles, if you increase the denominator, the value on the left decreases. Okay? So, we can only increase the concentration if we get to add more of a solute, or more of a solute, yes? The number of moles, if we increase the number of moles of a solute in our concentration or in our solution. So now in this case, this is what we call dilution. Are we together? Are we together? So now this is what we call dilution. You get to add more of the liquid so that you reduce the concentration. So basically, we call the concentrated solution to be what? So we have a concentrated solution which is called the stock solution. Okay, which you can now dilute by adding more of a liquid. So now what happens? So how do you get to determine the final concentration then after everything that we have? So we'll say, okay, initially we have that much, and we now want to find the concentration. So of course there's a general formula that we get to look at. Of course, it comes from the fact that in the first case there, you are able to determine the number of moles, right? As a product of concentration and volume. But you need to understand that even in the second case, the number of moles are still going to remain the same because we've not added any more solute, but we are just increasing what? The volume. So the concentration is going to change. You give it a C2. Then our volume is also going to change. So now, since we are saying the number of moles are going to remain the same, this gives us a new formula that we're talking about to be CV being equal to C2V2, or if you want, you can say MV M2V2, M2. So, okay, so what do you have as your initial concentration? You have 1.57, right? What do you have as your volume? Your volume is 1.50 liters. Not so. Then on the second part, we don't know the concentration, but we do know the volume, which is... What is the volume? The second volume is going to be what? Anyone with an idea there? I'm asking a question. What is going to be 1.5? 1.7. How have you come up with 1.7, madam? Okay, that's very good. So do we understand now? So initially you have 1.5 liters, and then you get to add more of that. So you expect that the volume is going to be increased, right? So before we get to add the two, we need to convert the cubic centimeters to liters by dividing by what? 1000, which is going to give us what? A 0.2. So 0.2 liters plus 1.50. That's how she's getting the 1.7 liters. Is there any question there? So now, at this point, you should be able to find or determine the second concentration, right? Not so. What are we going to have as our second concentration? So we are going to divide the first number of moles, which is a product of that. divided by what? The 1.70 from the other side. So these are just mathematical operations. We do understand where this is all coming from. We are just dividing on both sides. Any questions? So 1.57 multiplied by 1.50 divided by 1.7. 1.385. So now what are you looking at? Yeah. Okay, we had a minimum of 3 significant figures, right? So this is the most interesting part about chemistry, because yeah, there's that argument that you get to have. I like it. Unlike in physics, where as long as the solution is almost one and the same, they can still mark you. So for chemists, you need to be very, very careful with your rules of significant figures. And it should be part of you so that you take less than seconds for you to be able to determine which one has got the least number of significant figures. Okay. So are we okay with dilution? So if it was a lecture now, I'm sure by now you'd have done I don't know how many slides. So I'm sure you're used now. Okay. So now, guys, let's go back to this thing what we're talking about. We are talking about concentration, right? So initially, what did I say? I said molarity is just a section of concentration. Okay. Which focuses on you dividing moles in a liter. Are we together? Are we together? Wamino, are we together? Okay. Okay. So now, apart from these, we can talk about concentration in different forms. I said you can think about it in terms of mass. Instead of you talking about moles dissolved in a concentration, you can talk about mass. So instead of you saying moles per liter, for example, which is molarity, you can also say grams dissolved in a liter of a solution. This is one way of expressing concentration. And this is called mass concentration. Are we together? This is molarity. So molarity is called molar concentration. Are we together? Molar concentration. So molar concentration entails you're talking about molarity. Mass concentration entails you're talking about grams now dissolved in a volume of a solution. Any questions? Do we have questions? You mean like changing from okay, I think I don't know if I get it, if I've gotten your question or not. But what I'm trying to think of is okay, of course we can have, but that is under measurements, but not basically. Of course, for example, if you have 0.1 grams dissolved maybe in a liter, you can also convert this to, of course, since this is mass concentration because of the units that I'm using, right? So you can also convert that. The grams can be, you can have kilograms in a liter, or you can also change both. You can have kilogram, maybe you try to talk about a different volume, maybe cubic centimeters and whatnot. So all these conversions do exist, and I'm sure we do know how to go about it from the measurements. Not so? Okay, that's good, madam. So now there's this interesting question that I want us to answer. If we're able to answer this question, then I think we are done for tonight. Even as we prepare to talk about yes. You can mute your mic. No. Yeah, the answer is no. I'm sure you've seen some questions in your third sheet which was like, how many milliliters, for example? Such a question. How many milliliters? So it doesn't require you always to change or convert. In fact, it's not a requirement that you should convert, but we basically convert because we want to match up the units that we have in our calculations. So there's no way you can multiply molarity by cubic centimeters, so that's why we're basically converting. Not that it is a requirement. I don't know if that makes sense. Okay, we're okay to, well, we're good to move. Okay. So now listen, pay attention to this question as I write it. I'll write the equation. By the way, how is NS so far? How is NS? Are you enjoying it? Yeah, I like that. It's very simple. Do we have any different experiences, and maybe we are facing some challenges anywhere? Okay. Is it your first time attending one of our classes? The classes that I conduct? Is it your first time? Or maybe you've watched the tutorials on YouTube? Transcended. Have you watched any of our tutorials maybe? In case you've never attended our online classes as this one. Madam, you're the one who is saying that you have some challenges balancing the chemical equations in acidic and basic media. You've yeah, we have a channel Transcended. I don't know if you've seen it anywhere in the groups or maybe from your friends. So you've not done any of that. Okay. So now let's look at this question. We have that chemical equation there as a reaction. So now listen to the question. What volume? So the question is asking us to find the volume in liters of 2.5 molar concentration of sodium hydrogen carbonate is needed. So the question is saying what volume? Volume of that. So the volume of a sodium hydrogen carbonate, which is this one. So what volume of that in liters? They want it in liters. Is needed. Okay. What volume in liters of that? We have also been given that its concentration is 2.5 molar concentration. So you've been given the concentration. Now we want to find its volume needed to react completely. So needed to react with what? With the other reactant given in the question. So for this other reactant, we've been given that we had 0.025 liters of it, and we've also been told we had its concentration was 3.5 molar concentration. So now they want us to find what volume of the other reactant is needed to react completely with that given concentration and volume of the other reactant. Have we understood the question? The question says determine the volume of the sodium hydrogen carbonate, which is this one, okay, in liters, given that its concentration is 2.5. That is required to react with this other reactant of given volume and concentration. That is the question. We're trying to find the volume of the other reactant required to react with this other reactant where we've been given the volume and the concentration. Does that make sense? Okay. So now the equation, what information are we getting from the equation? We need to basically appreciate the information that we get from a balanced chemical equation by now. Mm-hmm. Okay, thank you very much. So Mr. Siame is saying that we get to get from the equation we get to get the more ratios, right? So if you look at the equation, we are told sodium hydrogen carbonate is in the ratio of 3 to 1 to the other reactants. Are we together? The citric acid. So they are in the ratio of 3 to 1. So they are in the ratio of 3 to 1. So if we can find the number of moles of this other reactant, we can find the number of moles required of sodium hydrogen carbonate. So now let's get to find the number of moles of this citric acid. So we said number of moles is given as a product of what? Concentration and volume, right? So for your own information, just know that concentration is number of moles over volume. So from that equation, you basically get to come up with your own equation depending on what you're looking for. In this case, we are looking for the number of moles, right? So therefore, our number of moles is going to be a product of the concentration and the volume. Our concentration in this case has been determined to be what? Our concentration has not even been determined, it has been given. Okay, 3.50. Then what is our volume? 0.025. So now my question is, was there any change to do any conversions in terms of our units in this case? Was there any need for us to do any conversions in terms of our units when we're multiplying the concentration and the volume? In the actual things. What do you mean by the actual things? The actual. You're using the word actual. Okay, thank you. So basically they're already matching up to make things easier. They're already matching up, not so. So we said molar concentration is more per liter, so we already have liters and liters, so no need of us doing any more conversions. So what do we get after multiplying the two? 3.5 by 0.025. Eight point 0.0875, or you are getting 8.75. Just right, it's basically 3.50, not 350. 3.50, just in case you're not able to say clearly. 3.50. Okay, so we have our number of moles here of what? Of a citric acid, which is this reactant. So now we can put it here under our ratios here. So now the question is, how many moles of the other reactant are required by looking at what we call the mole ratios. So when you cross and multiply, it will be like 3 times of that. So your value of x is going to be multiplied by 3 times that, which is going to be 0. What? 2625. So these are the number of moles of what? Sodium hydrogen carbonate required by the calculated number of moles of what? Of the citric acid. Any questions there? Have we understood? You get to look at the ratios of what you're interested in. So assuming, madam, in this case, we were asked to find maybe how much of the sodium, this one here, this other reactant. Imagine you were asked to find how much of that was produced. So you're going to see that we are in the ratio of 1 to 1. You look at the ratios. So you come out, you say 1 to 1, then put the number of moles under the actual reactant or product. So for example, in this case, we are talking about now, we're interested in sodium hydrogen carbonate and the citric acid. So these guys are in the ratio of 1 to 3. So we've written the ratio 3 to 1. 1 representing the citric acid, which we've determined the number of moles. So I've put the number of moles, each number of moles under the 1 there. Then we're crossing to multiply using the same mole ratios to find the number of moles of the sodium hydrogen carbonate required.
Sir, I have a question. Is concentration always moles per liter? Let's consider what volume is units of both 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 liter both.
Cubic meters?
Okay, let's say yeah, cubic meters. Was concentration still going to be more per liters or moles per deciliter?
Okay. Let's do this, Nancy. Okay, let me just finish up this question, then I'll explain more about that. Is that okay? Yes. So now we have the number of moles for our sodium hydrogen carbonate required by the calculated number of moles of fat, the citric acid. So now our question is asking us to find the volume, right? We have the concentration, we now have a number of moles. What are we supposed to do for us to find the volume?
Don't use the same formula and then you just use volume the subject of the formula. I just number of moles per liter.
Okay, so concentration is equal to number of moles over volume. You can make volume a subject, but in this case I would go for a formula that is straightforward. Oh, there's no formula I'm going to use. So 2.50 is moles per liter, right? Since we are saying okay, liter. That is our molar concentration, which is this concentration. Now we have the number of moles there. What do we want to do? We are interested in finding the volume in a liter. So what we are interested in should be on top. So we need to have a reciprocal of that. So we're going to have 1 liter on top over what? Over 2.5 moles. So I'm trying to show you how you can work without a formula. So now multiply by what? The number of moles, so that they can cancel out with a moles down there. 0.2625. In other terms, what we are doing is basically what you told me. You said volume is going to be, if you make volume your subject, it's going to be what? Number of moles over what? Concentration, right? Which is basically what we have. So what are you going to have as the solution there? What do you have as the concentration? Zero point. Isn't that too big? Zero point 0.265 divided by 2.50. Get the actual figure that I have. What are you doing, guys? 0.2. Look at this. 0.2625 divided by 2.50. Do that again. What calculator? What calculators are you using? I've said 0.2625 divided by 2.50. But where were you getting 1.7? Hmm? Okay, so we have 0.105, right? As our liters. But then, go back to the question. If you go back to the question, the ones that I gave you, the least number of significant figures that we had, basically we had 0.025, which had 2 significant figures. Okay? So now, is it okay to leave our solution as it is? The least one at 0.025. Is it okay to leave our solution as it is given there? Okay. So now if you go by the rules, yeah, These rules are very fun. They'll tell you to say no, you can look at two significant figures, so it's going to be 0.11 liters. But then, if you basically get to compare 0.105 and 0.11, don't you think there is a very big difference, sir? Don't you think there's a big difference? Isn't that like overestimation? You're exaggerating your figures. So you find that these same lecturers will tell you that your solution is supposed to be 0.10. It's fine like that. So they are more interested in you basically getting to round off when usually the value is maybe 6. But of course they'll tell you 5. So go by their rules, which is going to be 0.11 liters. Okay, questions? Before I get to I get to respond to Nancy's question on the issue of the volume there. The questions. Okay, Madam. Yeah, Madamu. Madam Natasha. You should even make sure you register for classes just before you go, actually. I do meet up with my students every day at 13 hours, and also we have these classes at 19 every day. So you can make sure you register. We are transcended, just in case you forget the name. Oh, you're from Hebron on. Oh, wow. Okay. Okay. So now, okay. So you can be attending the online classes at 19 every day. That's very fine. It's okay. Okay. Then if you can make it on the weekends, you can come through. So now, okay. So I'll send the questions to the group and the notes that I was using the group as well. To answer to respond to you, Nancy's question on the issue of the volume. Volume is not necessarily going to be given in moles per liter. There are going to be cases where they'll tell you mole per cubic centimeters and whatnot. So what is important, that's what I was saying. When you are working with the issue of you determining the number of moles and whatnot, I advise you going by the dimension analysis, right? So for example, if I were to give you 0.1 liters, so it's up to you to look at what you have. So now in this case, they ask you to find the number of moles. So what are you going to do? Are you going to just multiply just because I said when you have liters, no need of you converting? No. Look at the units in which the concentration is given. It is in cubic centimeters. So you'd want to multiply by something that is going to like cancel out the cubic centimeters. So you can multiply by the liters. And you'd want to make sure that you convert the liters to cubic centimeters. So look at the units that you have. And it's very possible to have cubic meters as well. So make sure you know how to convert these units. So 1 cubic meter is equivalent to 1,000 liters or 1,000 decimeter cubed. And 1 cubic meter is equivalent to what? A million what? Cubic centimeters. Any questions there before we end our class? Next. Alright, so next time we meet, we'll talk about in fact, I'll send the tutorial to the registered students group. Precipitation reactions. Watch a video on precipitation reactions. If you have questions, send them to me. Then, of course, in the registered students group, because I don't allow people inboxing me. Then, on that note, next time we meet for a class online in chemistry, we're going to proceed and look at the balancing of the chemical equations using oxidation numbers, ion electron method, and I'm sure you'll be good to go. So, as you look at precipitation reactions, make sure you look at the solubility rules as well. I'll share both videos. So I think it's a good night for now. Make sure you get in touch if you've not yet registered, because I just invited you tonight to attend without registering. Thank you.